Okay, folks, today's lecture is a little bit more on geologic time, focusing on something that we call absolute dating. So when we're talking about absolute dating, we're talking about putting absolute ages on these rocks. If you look back through the fossil record, starting from the top and going down, which as we know from when we talked about relative dating, while talking about sedimentary rocks, we know that as we go down in the rock record, rocks get older, right? Because new rocks are deposited generally on top of older rocks. So if we dig down through a big section of sedimentary rocks, we might see the fossils in those rocks change gradually from rocks that are, or from fossils that are more familiar to us, saber-toothed tigers and mammoths, to fossils that are gradually less and less similar to the sorts of animals that we know. So some strange mammals. And then before this, the Mesozoic, Cenozoic boundary here, we have dinosaurs that we start to find and ferns from long dead plants. And then from before the Triassic, we get into some really strange animals and plants. Sometimes it can be really difficult to tell even if it's an animal or it's a plant, just looking at the fossils. And so we see things like trilobites way back here, which look like weird little bugs, like pill bugs or horseshoe crabs, sort of, that used to live on the seafloor. We need a way in which to determine when these fossilized organisms live. We can't do that just by looking at the fossils. The fossils can tell us relative ages by using what layers they're in to compare that certain fossils are found in older or younger layers than other fossils. But it doesn't tell us the numbers. So how do we get these sorts of actual numbers of millions of years ago when we're looking at rocks like this? We'll talk a lot about that today. And then we'll talk a little bit more about some of these fossils and fossilization and some particular fossil finds, just to round out our discussion of geologic dating. So this first lecture is going to focus on absolute dating and radioactive isotopes, which are what we use to track the absolute age of rocks. And then later we'll talk about the geologic timescale and fossil preservation in this particular place. I've got a video to show you from another lecture series on the Burgess Shale, which is a really great fossil find in Canada. So when we talk about geologic dating, we can break it up into absolute dating and relative dating. What is the difference between these two? Sounds like a good sort of question for an exam, say. So absolute means that we are coming up with an absolute number. It's a number that you're coming up with of years ago. Whereas relative dating is just you're figuring out the age relative to something else. So that means that you're finding out whether a fossil or a rock layer is older or younger than something else. And so we've talked a little bit about relative dating already. So let's fill this in. What sorts of things do we use when we are thinking about relative dating in rocks? We use what we called Steno's laws, if you remember those. Also known as the principles of stratigraphy. And these were things like the law or the principle of original horizontality, which tells us that rocks that have been folded used to be flat, because rocks are deposited flat. So that folding, that tilting must have happened later. Like the superposition, principle of superposition, which is what we use to determine that rocks on top are younger than rocks below, right? So these are generally what we're doing here. And also fossils fall into this category too. Fossils don't tell us an absolute age unless we get that absolute age from somewhere else, but they can tell us the relative age. So once a fossil organism has died off, it's not going to show up in the rock record again. And so we can use where we've recorded those fossils happening in different other layers across Earth's surface to date a new layer of rock if we find fossils in it. Absolute dating, we don't use principles of stratigraphy to tell us the absolute ages. We don't use fossils to tell us the absolute age unless we have already assigned a number to those fossils using one of these other absolute dating techniques, which are all based on radioactive isotopes. And we might call the act of using radioactive isotopes to do absolute dating, you might also see it referred to as radiometric dating. So let's talk about that a little bit. How do we know the numerical ages of these rocks? How do we get these absolute ages? Well, we use radioactive isotopes and their known decay rates. We know how fast a certain radioactive isotope decays, so we can use it as a clock. So when you see clocks and rocks, think radioactive isotopes and their known decay rates. Let's get into that. Radioactive decay is the act of one nucleus of an atom. So we see nuclei diagram down here, right? And we remember from when we were talking about atoms way earlier in the course that the nuclei of the atoms contain some protons, they contain some neutrons. The protons have positive charge, the neutrons have net zero charge. These are sometimes stable. Some atoms, some isotopes of certain elements are stable and they don't decay. But some isotopes, certain isotopes, do decay. They are unstable, which means that they break down. And conveniently for us, they do that at a set rate. Because we can figure out what that rate is and that rate stays the same over all geologic history, we can extrapolate from the number of these radioactive isotopes that are in a rock to figure out how old it is. Radioactive decay is the process of one nucleus breaking down in some way and releasing particles and changing into an entirely different nucleus. Usually, this means that they become new elements entirely, either because they release something that contains some protons, or in weird cases, they can even release a neutron can turn into a proton and an electron, which is getting into some weird physics. But if you release that electron, now you're left with a different number of protons than you started with. All in all, the reason that we are changing elements, if we connect that back to what we already know about elements, you change your element, that means you must have somehow changed the number of protons in your nucleus. And that is most of what we're talking about when we're talking about radioactive decay. We're talking about changing the number of protons and sometimes also neutrons in the nucleus. And they do that by releasing particles. Those particles zip off with really high speeds, really high energies, and that is what we call radiation. If you get hit by some of those particles, enough of those particles, it damages your skin, it damages your DNA, it can damage other parts of your body as well. And that's why when we talk about radiation being dangerous, it's because they are these particles flying off really fast from all these different nuclei at once, hitting you, breaking down the chemical parts of your body. But we're not going to talk too much about the dangers of radiation. We are instead going to use that little bit of natural radiation that is present in some nuclei to figure out the age of rocks. As I said, most isotopes are stable and don't decay, or at least they decay so very slowly that we've never been able to measure them decaying. So some stable isotopes that you've seen already are like carbon-12 and carbon-13. These are the common isotopes of carbon, and only certain ones are unstable. So in the case of carbon, it's only the carbon-14 that we see in any real quantities on Earth, and there's just a tiny little bit of it, and it decays because it is an unstable nucleus. We're not going to worry about why a particular nucleus is stable or not. That's really the realm of nuclear physics. So we're going to avoid talking about that. But you do need to know that certain isotopes of certain elements are unstable, aka radioactive. They can release radiation. And so let's talk about that example, carbon-14. The way that it decays, so carbon-14, let's go back and figure out exactly what its nucleus is made of. So if you look at your periodic table, you can figure out that carbon has an atomic number of 6, which is the number of protons. And since protons plus neutrons has to add up to 14, that means it must have 8 neutrons in it. So we've got this nucleus of 1, 2, 3, 4, 5, 6 protons and 1, 2, 3, 4, 5, 6, 7, 8 neutrons. Looks good to me. And because it is unstable, sometimes one of those neutrons in carbon-14 can become a proton and an electron, and the electron is emitted as radioactivity. You ever hear about beta radiation? That's actually releasing really fast electrons that were originally part of a neutron in the nucleus. Weird that neutrons can actually turn into protons and electrons. And again, that's nuclear physics that we're not going to worry about. But that is how we turn this nucleus that originally had 6 protons and 8 neutrons into one that's got 7 protons and 7 neutrons. So we've changed the atomic number, which means we've changed the element. It still has the same number of protons plus neutrons in it, so it stays with the same mass. And it releases that electron as what we call a beta particle, or beta radiation. The unique thing about carbon's decay is that it's got a set rate of decay where, on average, it will decay with 50% probability, so it has half a chance of decaying every 5,730 years. That's what we call its half-life. Let's think a little bit more about what that means. Talking about a single nucleus, when we are talking about half-life, that is the time over which it has a 50% or half chance of decaying. So if it doesn't decay in this 5,730 years, it might decay in the next 5,730 years, again with 50-50 probability that it's going to happen for any one nucleus. Now, the interesting thing is that if you have then a whole lot of these nuclei, let's say you have 1 billion of them, well, on average, 50% of those are going to decay every 5,730 years, and 50% of them are not. So if you start with 1 billion of them, you are going to be left with just about 500 million that have decayed and 500 million that have not decayed after every 5,730 years, after every half-life. So another meaning of half-life is the time over which it takes for half of your nuclei to decay, and the other half stays as whatever nucleus it started out as. So connecting that to our carbon-14 and nitrogen-14, if you start with 1 billion carbon-14s, after 5,730 years, you are going to have about 500 million carbon-14s, and the other 500 million are going to be nitrogen-14s. And it's carbon-14 has this particular half, 5,730 years. Other nuclei have different half-lives. Some are very short, seconds or milliseconds or microseconds or even less time, and some are very long. Some take billions of years to 50% decay. So to review that, half-life is the time over which a certain isotope has a 50% chance to decay, like a coin flip, right? Heads or tails. Also, if you have many of that isotope in a sample, about half will decay over one half-life. So that half-life ends up actually having 2 meanings there. Let's think about what that means in a quantitative sense. So on this graph we're going to be plotting the amount of a particular radioactive isotope we have after a certain number of half-lives have passed. So we start out with no half-lives have passed, and we start out with 100% of what we start with. Makes sense. How much will be left after one half-life? What's your thought? Hopefully you came up with 50%, right? You cut that in half after one half-life, you're down to 50%. How much will be left after 2 half-lives? Initially, some people will think that, oh, if you lost 50% in that first half-life, then you'll lose the other 50%, you'll be down to 0. But that's not what happens, because you sort of reset that clock with your 50% remaining after one half-life, and half of that now is going to decay after 2 half-lives. So you actually go to 25%. You cut that in half and you go to 25%. After another half-life, you cut that in half again to 12.5%. And then you cut it in half again over the next half-life to 6.25%. And so on. So every half-life, you cut the amount that you started with in half, over and over and over. And so if you want to think of it in terms of percentages, you can think of it in terms of percentages. You can think of it in terms of fractions as well. Half is left after one half-life. What's half of a half? That's a quarter. That's how much is left after two half-lives. What's half of that? It's 1/8 after three half-lives. Then it's 1/16 after four half-lives. Either way, every half-life you go, you cut it in half again. What about in between? What if only 1.5 half-lives have passed? Well, then you can extrapolate it from a graph like this. Or if you are comfortable with logarithms and exponential equations, there's an equation to use. We're going to avoid touching that too much in here because I don't want to teach exponentials and algebra 2 stuff over again to those that may have forgotten it at this point. Instead, we might interpret on a graph. So if you looked at a graph that was like this, and I asked you, how much is left after about 1.5 half-lives? So you would need to look at this and say, okay, this is 1.5 half-lives. And here's where it intersects on the graph. And so reading that graph with, as accurate or inaccurate as this graph is, you'd probably say, oh, about 35% is left after 1.5 half-lives. What about after 0.5 half-lives? Could do that again up here. Maybe that's about 70% is left after 0.5 half-lives. And you could do that with any point on the graph as accurate as you can be. You could also go the other way. If I said you had 20% of your original parent isotope, that original radioactive isotope you started with, how long has passed? How many half-lives? You'd start with 20%. You'd read that all the way over here. And then you'd say, oh, what is that? Maybe that's about 2.3 half-lives. I do want you to be comfortable reading a graph that looks like this, and we'll go over that a little bit in lab. So I used a term in that last slide where I said parent isotopes. Let's talk about what parent isotopes are and what daughter isotopes are. So when a radioactive parent isotope breaks down, it releases radiation and it leaves behind a daughter isotope. Often that daughter isotope is a stable isotope. The parent isotope is always radioactive, and it breaks down into the daughter isotope, which tends to be stable. So when we talk about those two things, I want you to recognize what is a parent and what is a daughter, and be able to tell me that the parent isotope is the radioactive one, the daughter isotope is the stable one. On that last graph, we were counting the amount of parent isotopes, but we could have flipped it and talked about the amount of daughter isotopes too, couldn't we? So if you started with 0% daughter, then after one half-life, since 50% is parent, 50% would be daughter. And after two half-lives, well, 25% is parent, so 2 half-lives, 25% is parent, so 75% must be daughter, and on until you get to, you approach 100% way out there. And we already mentioned what the radiation is. It's the high energy particle, a tiny piece of matter and energy that flies away from a nucleus. It's got a lot of energy, and that radiation can do damage to other things. We always encounter some radiation in our daily lives. We are surrounded by small amounts of radioactive isotopes, but we have mechanisms in our body to do things like repair damaged DNA or get rid of cells that die because their DNA is damaged. And so usually our bodies can deal with that normal level of radioactivity. It's only when we concentrate radioactivity in one spot, because let's say we enrich a bunch of uranium or we explode a nuclear bomb, and that's when you have a lot of radiation in one place, that's when it gets scary. Let's talk about some examples. These are some that you might see discussed when talking about the absolute ages of certain materials. Each pair has a particular parent and a particular daughter isotope. Parent is the radioactive one, the daughter is the stable one. And we can see some common ones. We've already talked about carbon-14 and nitrogen-14, which has a half-life of 5,730 years. There are other ones like rubidium and strontium. That's got a half-life, rubidium-87 that is, has a half-life of 47 billion years, really long. Potassium-40, anything that has potassium in it has a little bit of potassium-40 in it. So feldspars are a tiny bit radioactive always. Bananas are a tiny bit radioactive always, but not so much that I think I did a quick calculation once, and it was you have to eat about 1,000 bananas a day for it to be dangerous to you. And at that point, you have other problems. So you don't need to worry about the potassium in bananas because it's radioactive, but there is a little bit of natural radioactivity in bananas, which have a lot of potassium in it. Potassium-40 breaks down into argon-40 with a half-life of about 1.3 billion years. And then there are two different isotopes of uranium that decay to two different isotopes of lead, and those have billions of years of half-lives. Right? So a lot of these are very long, these pairs. We have them on this list because they're useful in dating really old rocks. And then this one, carbon-14, has a half-life of 5,730 years. Because they have different half-lives, they are useful in dating different things of different ages. That is, parents with long half-lives are more useful in dating older things because there's still a little bit of the parent remaining. You wouldn't use carbon-14 to date a billion-year-old rock because almost all of the carbon-14 would have broken down. You wouldn't use uranium-238 to date something that was only a few thousand years old because only a little bit of it is broken down and it would be difficult to measure just how much. So we can look at the half-life and we can compare it to the effective dating range, that is the range over which that isotope pair is useful for getting an age date. Something like carbon-14 is useful for things that are hundreds of years old to tens of thousands of years old. So it's useful. Carbon-14, we hear about it a lot when we're talking about ancient humans because it's useful over the time scale in which humans have evolved and developed civilization and cities. And so we can use it to date things like ancient pieces of pottery that are a few thousand years old because it matches well with the half-life of carbon-14. That's the only reason. And because there's some carbon around in stuff that old people were using, right? The pottery probably had some old milk in it or beer or some food, and that's got a lot of carbon in it. So oftentimes there's carbon around for us to do the dating with. If not that, then in living material, right? It's useful for dating things like wood or charcoal or bone and tissue or calcium carbonate shells that certainly have a lot of carbon in them. But we can't use it to date rocks that are millions of years old because most of the carbon-14 has already broken down after millions of years. Instead, we would use one of these other pairs. So these ones tend to be more like millions to billions of years because their half-lives are in the range of billions of years. If you wanted to date something that was a few million years old, you might have a tough time with some of these pairs here. So you might pick some other pair to get something that's just a few million years old. Moreover, these parent and daughter isotopes do get stuck just a little bit in certain minerals that are common. So common minerals and igneous rocks include things, right, like muscovite and biotite and hornblende and potassium feldspar. So there are certain isotopes that appear very often in those. So they're useful to date those igneous rocks. Another mineral in here that often gets talked about are zircons, because zircons, when they form at really high temperature, and then they really hold on to whatever atoms they've started with. They don't weather very easily, so that any uranium that gets locked into that zircon stays in that zircon. And when it breaks down into lead, even that lead sticks around. So because it's not adding or removing isotopes over its life, it's a pretty good inventory of the isotopes that were originally in that mineral. So zircons are useful both because they appear in igneous rocks and because they hold on to isotopes really well. We should talk about when you can use isotopes to date particular materials. To use a particular parent-daughter pair of isotopes, a sample must be old enough for measurable decay to have started. That's maybe on the order of 1% of a half-life. So for something like carbon-14, whose half-life you should be familiar with, of about 5,700 years, you're not going to use it to date something that's younger than tens of years, right? 50-some years old, because we won't have measured enough decay to really get a sense of how old it is. So if it's hundreds of years, we're good. If it's thousands of years, we're good. If it's tens of thousands of years, it's starting to get a little long for some of it, but we can use this as long as we have a measurable amount of parent left, which really tends to disappear after about 10 half-lives. So after about 60,000 years or 70,000 years, a little more than 10 half-lives, carbon-14 doesn't give us much in terms of radiometric dating, because most of the carbon is already gone. Okay, let's think about another condition that we need, and we'll do this as an example. Let's say we have a sample and we count 250 parent isotopes in there. So we counted 250 carbon-14s. It could be the case that we started with 250 parents and it's 0 half-lives old, or it could have started with 500 parents and it's 1 half-life old. Or it could have started with 1,000 parents and 2 half-lives old. All of these conditions would leave us with 250 parent isotopes. Could be between those numbers, could be more half-lives. How do we know which of these is true? What do you think? What would you need to measure to figure out which of these is true? We don't have another way to measure the age of these rocks. We've got to use the isotopes that we have available, because that's the only way to get the absolute age. So what do we have to do? We have to count the daughter isotopes as well. So in the case of carbon-14, its daughter isotope is nitrogen-14. So we would need to figure out a way to count the nitrogen in that sample too. And if we found that there was no nitrogen in the 250 parents, we could safely say that it was 0 half-lives. If it was 250 and 250, it would be 1 half-life. It's 750 and 250, because it's 3-to-1 ratio, because 75% is daughters and 25% is parents, we know that it's cut in half twice. And that's how we get to 2 half-lives here. So remember that the number of parents plus the number of daughters equals how many parents you started with, at least in terms of isotopes, right? This is talking about isotopes, not people. So here's our graph again. These are the parent isotopes. They're decaying over time. And here are the daughter isotopes. They're accumulating, they're concentrating over time. At the start, you have 100% parent and 0% daughter. After 1 half-life, it's 50-50, a 1-to-1 ratio. After 2 half-lives, you have 1/4 of the parent remaining, right? You cut it in half twice. To make a whole, you need the 3/4 to be the daughter. So it's 1/4 parent, 3/4 daughter after 2 half-lives. That's a 1-to-3 ratio. After 3 half-lives, you'd have 1/8 parent, and the remainder, 7/8, would be daughter. That's a 1-to-7 ratio. So using a graph like this, we could figure out, just by using the ratio of parents to daughters, how old something is in terms of the number of half-lives. Then if we know the half-life of that isotope, which we do, because we've spent a long time measuring all these different things, we can actually use that number of half-lives to figure out just how old something is in terms of years. Like we saw from that graph, the ratio of parent to daughter isotopes can be used to tell you how many half-lives have passed. Once you know this and the half-life of your isotope, you can know the age of a sample. So the age is going to be equal to the number of half-lives, 1, 2, 3, 1.5, times the half-life in terms of years. So for example, if we had something that was the ratio was 1 carbon-14 to 3 nitrogen-14, our ratio is 1-to-3. From that graph that we were looking at, we know that it should have all started out as carbon-14, it's cut in half, and then it's cut in half again, giving us this 3-to-1 ratio. We can use this plus that graph to get that this is 2 half-lives. To figure out the age, then we need to multiply that by the half-life of carbon-14, 5,730 years. And we would get the age of that sample, 11,460 years old. That's how you do that sort of math. It's just a multiplication. Think about it for a second. What other criteria do you think we would have to meet to be able to use radioactive dating on a sample? In our carbon-14 example, we have been assuming implicitly that we started with no nitrogen. We've also been assuming that we didn't lose some of those isotopes or gain some of those isotopes over time, which would mess up our age dating. So thinking about that, we can think, okay, we can't gain or lose parents or daughters over time, except by changing into one, from one into each other by decay. We can have parents change into daughters, but we can't have parents leave our sample or get added to our sample. We can't have daughters leave our sample or get added to our sample. So we want those minerals like zircons that hold on to whatever nuclei they've got, that don't release those atoms because they weather easily. You want to have a sample that's not really well weathered, so fresh samples are better. Also, sedimentary rocks, they're made of old particles, right? They're made of pieces of other rocks, at least clastic ones are. Right? We talked about how sedimentary rocks are made of clasts, pieces of old rocks. So if you measure their age, you're really measuring the age at which those minerals formed and locked in those nuclei. So you're really measuring the age of the original rock, the age of the clast. So I can sort of put an upper bound on how old your sedimentary rock can be. But the sediment itself might have formed right after the igneous rock did, or it may have taken hundreds of millions of years to form that sedimentary rock from the original igneous rock. You'd have to do some more work to figure it out if you are looking in a sedimentary rock.